I want to do one more brief video because I was not really satisfied with the way that I taught transition matrices the other day. I don't think I really did a good job explaining it. So I want to do one example, and this is off the homework, so you have a freebie here. It says to do a transition matrix from the basis, the first basis is 3, -1, comma, 1, 1, and we want to transition to a new basis, which is 2, 5, comma, 1, 2. So, how do we do this? Well, the key to it is to say we need to write the old vectors in terms of the new vectors. Now, I was tempted to just say like, oh, maybe we'll just cut this section from the class or just not put it on the final, but it's on the final. The syllabus is set. I feel like this topic is pretty important, so I can't just skip it. So here is what you need to remember. This is easy to mix up which way we're supposed to go. So this is just the most concise way I can describe it. Write the old vectors in terms of the new vectors. So we want to say 3, -1. The old basis vector has got to be some constant 2, 5 plus some other constant 1, 2. That's the idea. I want to find the coordinates there, C1 and C2, so that we can change it. But now what about the other vector? We need to write 1, 1 in terms of some other D1, 2, 5, plus D2, 1, 2. So each of these, and there's more than one way to solve it, but each of these can be done as an augmented matrix. We have the coefficients 2, 5, 1, 2. And then we need to do one system where we set equal to 3, -1, another where we set equal to 1, 1. But since we have the same coefficient matrix, we can do what I might call a double augmented matrix, which would be, I'll put 3, -1, and then 1, 1. As we said that way back in the first chapter, that if we're setting the same matrix, solving for two different targets like this, we just put 2 columns in a row and solve them both at once. As we RF, the left side will become the identity matrix, and then the right side will become our coefficients for both answers. -7, 17, -1, 3 is what we get when we row reduce this matrix. And so that means those are our coefficients. If we plug in -7 and -1 here, and go ahead and... Oh, sorry, no, that's not right. It's -7 and 17. Right, each column is the solution set, not each row. -7 and 17, and check that out. That's -14 plus 17 is 3, -35 plus 34 is -1, and then this would be D1 would be -1, and this would be 3. And you can check that again and show that that also works. So then our transition matrix is this guy. It is the columns that we've just found, the solutions, coordinates for each of the old vectors. So we're saying that if you wanted to go to the same spot as 3, -1, that whatever this new system is, it's 2, 5, and 1, 2, you would go -7 in the direction 2, 5, and then 17 in the direction 1, 2. And somehow you'd end up landing at the same spot. So yeah, you solve both of these. You write the old vectors in terms of new vectors. You solve to find the coordinates, which are the C1 and C2. So for all of them, and those solutions are the columns of your transition matrix. And so that means if you are given, as this problem says, if you have 3, -1 in the old system, you would then multiply by this transition matrix, which gives you -20, 48 in the new system. So that just tells you that the x in the original system was 3, -1. X in the new system, oh, that shouldn't be there, is -20, 48. All right, hope that helps.